Okay, everybody, this is the video tutorial about critical angle. All right, and this is sort of an application of refraction, which is the bending of light when light travels from one medium, let's say air, into another medium, let's say glass or water. All right. And the page references that you see here refer to the grade 10 textbook that we're using. And throughout this video tutorial, you'll need to take some notes, draw some images. You're going to need your scientific calculator to do the problems. And we're just going to go ahead and do that. So go ahead and get out some paper, write down the title of critical angle, get out your scientific calculator. Now, I suppose you could use your cell phone, but just, keeping in mind that when it comes to the actual quiz or test or exam, you're not going to be able to use the cell phone. You're going to have to rely on the scientific calculator itself. Okay, so you want to learn how to use your calculator, in other words. Okay, so let's talk about this thing called critical angle. So I'm going to move to the first slide in the presentation here, if I can. Okay, so this is a little bit of a review about refraction, which will set up this concept of critical angle. When light travels from a medium, a substance, a material, with a higher index of refraction to a medium with a lower index of refraction. So in other words, if it was traveling from water to air, let me get my pen going here. All right. If light was traveling here from the water and it was moving into air, okay, so it's going from water into air, it's going to bend away from the normal. All right, and we've seen this already in refraction when it does this kind of thing, when it goes from a more dense or, something with an index of refraction n, this one, let's say n1, and this is n2, a different index of refraction. When it's going from a more dense or a higher index of refraction to a medium with a lower index of refraction, it's going to bend away from the normal. And we've seen this. Now, this, of course, here is the normal line right there, that dotted line. And this is the interface here between the two media. And, of course, I'm giving you the page reference as well, figure, so you can actually look at this in the textbook as well. So this is not surprising. This right here would be the angle of incidence, and we often write that as theta I or theta 1. And this right here between the normal and the refracted ray is theta 2 or theta r. This is the angle of refraction. So the ray, instead of traveling straight and going up like this, bends away from the normal, and this is called refraction. All right. Now this is a review. We already know this, but we are going to see something about critical angle in a moment. So let's move on. As the angle of incidence, all right, that is this angle down here, as the angle of incidence increases, the angle of refraction also increases. So here's a particular angle of incidence, and maybe the ray bends this way, all right? As we keep increasing this angle of incidence, the refracted ray bends here, and then eventually it gets to a point where the angle of refraction is 90 degrees. You see? And that 90 degrees, let me erase that for a second. Let me go to a different color. It is 90 degrees right here with respect to the normal. So this angle here, that's the angle of refraction, right? It is now 90 degrees to the normal. Okay, so when we get to a particular angle of incidence where the angle of refraction is 90 degrees, this is called the critical angle. The critical angle is the angle of incidence which creates an angle of refraction that is 90 degrees to the normal. Because in the past we had stuff like this, there's the incident ray, and we bent away from the normal. If you keep increasing this angle of incidence, eventually the ray will go 90 degrees to the normal. And that's called the critical angle. If, however, the angle of incidence is greater than the critical angle, All right, so here you can see I've drawn this a little bit more than it was before. Like before, it was kind of coming up here. All right, there was the angle, the incident ray and the angle of incidence. If we go beyond the point where the incident ray or the angle of incidence would cause an angle of refraction that was 90, if we go beyond that here, as in this red arrow here, the angle, the incident ray, then the light actually is reflected inside the medium. The refracted ray, instead of skimming along the surface or even coming out, okay, or when it's the critical angle, it skims along the surface. When you increase it, the ray actually refracts inside. It bounces inside. This is called total internal reflection. And total internal reflection, this is reflection, right? Imagine this is a mirror right here, right? And you bounced a ray here, it would bounce off, right? But, you know, if it's not a mirror, if it's just going between water and air, you would expect that it would bend away from the normal if it's going from a higher index to a lower index of refraction. And at the critical angle, it just skims along the surface. But if you go beyond that, the refracted ray bounces back inside. It actually acts like it's reflecting, all right, sort of hitting the surface and bouncing in. And this is called total internal reflection. So total internal reflection occurs at an angle of incidence that is greater than the critical angle. All right, so let's go on. Now, how could this be used? What are some applications? So once again, hopefully you're writing this stuff down as we work through it, and then we'll do some problem calculations, all right? Light travels very fast, all right? And it can travel very far in a fiber optic cable using the principle of total internal reflection. So think about a fiber optic cable that is used in medical imaging, all right? So I'm going to get you to write this stuff down. And you don't have to draw the pictures, of course, but they're in the textbook as well. If we look over here at this image here, we can see that this is a camera of sorts with a tube that goes down to here. And this would be inserted, say, through the mouth and down the esophagus and through the stomach and into the small intestine or duodenum in order to view areas. Now, you cannot swallow the video camera that I'm using right here to take this video, all right, or a typical camera, all right? But a tube that could snake down through the human body can see things that a regular camera can't. But in order to do that, you're going to need the image or light to be able to travel through that tube. And it does this using the principle of total internal reflection. Like imagine, let's come over here and look at this picture here. All right, here you can see in yellow or orange an incident ray inside a fiber optic tube. All right, this has a higher index of refraction here than here. So depending on the angle, the ray of light could just come out and bend. There will be refraction. But if this angle happens to be greater than the critical angle, the ray bounces inside. And then it hits the side and it stays bouncing inside. And this is how we can keep light waves or whatever inside the actual cable. So this is an application of total internal reflection. And as you can see, it can get rather complex, and we're not going to do that in the grade 10 course. Okay, let's go on. Now, I do not work for the telecom companies, and I don't know all of the details about this, but this is a map showing some fiber optic or internet cables that travel very far distances. As you can see, we've got the United States here, and we can go all the way under the ocean. All right, now in order to do this, we need to pass a signal, whether it's light or something like that, through fiber optic cables. And again, without getting into all the details, and there's quite a bit of details when you look at the actual construction of the fibers and their thickness and what they're made of, all right? If you go into physics or engineering, you know, you would learn this kind of thing. But these cables are used to carry signals great distances, and this uses the concept of total internal reflection to keep the light inside a cable. And think about it this way. I mean, if you think, well, what's the purpose of light? What can that do when it goes through a cable and gets to the other end? What kind of a signal is that? Well, think of flashing a flashlight at somebody across a great distance. If you flashed it with some kind of like Morse code, or turned it on and off really rapidly, 3 ons followed by a pause and then 2 ons, that could be a signal, right? So somehow computers or whatever could analyze that signal, and it's now a message. So again, the take-home message from this is not to know all the details, but just have appreciation that this concept of total internal reflection can keep light inside a tube, bouncing around, until it goes a very far distance. Okay, and I've got some demos that I can show you in class. You can also look this up on the internet to learn a little bit more about this, and especially on YouTube, you can see videos illustrating this. Okay. So we are going to do some problems. We are going to mathematically determine the critical angle. So continue to write this down. And if you have to pause the video every once in a while so you can get it down, that's fine, all right? So to mathematically determine the critical angle, which is the angle of incidence, the critical angle is the angle of incidence at which the angle of refraction is 90 degrees. We need an equation to solve for this. Let me show it to you, and you'll see how similar it is to something that we've done before. Okay, so we're going to write down this equation. And you will see that it is N1 sine theta C. That means instead of sine theta 1 or sine theta I, the sine of the angle of incidence, this is the sine of the critical angle, because this is what we're going to solve for. So the index of refraction of the first medium that the light is in times the sine of the critical angle equals the index of refraction of medium 2 times the sine of 90. Now, in the past, we wrote theta 2 or perhaps theta r. We said that's the angle of refraction. Well, for the critical angle, we want the index of refraction to be 90 because we said, there's the incident ray and we want this. We want it to go, horizontally along that, interface between the two media. Here's N1 and here's N2. Okay, so this is theta C, the critical angle. And this, of course, is going to be theta R. All right, which is going to be 90 degrees. So what is the angle of incidence, the critical angle, depending on what the substance is in order to get a 90-degree angle of refraction? Depending on the substances, what is the critical angle you need to get the ray to do this? And then, of course, we're going to figure out, well, what's the angle to get it to do total internal reflection? Okay, so here's another equation for you to learn. Okay, there's about 4 or 5 of them in this optics section. All right, don't forget, by the way, you'll have N equals C over V. The index of refraction is equal to the ratio between the speed of light in a vacuum divided by the speed of light in the particular medium. You'll have the index of refraction is equal to the sine of the angle of incidence divided by the sine of the angle of refraction. We've got that. We've got Snell's law, N1 sine theta 1 or I equals N2 sine theta 2, and you can solve for any of these variables. And now we have this one. All right? Okay, let's go on. Okay, so in order to solve for theta C, the critical angle, we are going to rearrange this. So we want to isolate this and get this alone. So we are going to have N2 sine of 90 divided by N1. We can just break this apart and bring it under. But when we split up the sine from the theta C, we are going to get the inverse sine. So you're going to use second function sine on your calculator. Most likely that's how it's going to work for you. Okay? So get that down, and then let's see what our problems are like. Okay, so copy the example problems. Good to have all these things in your notes. Example 1. Calculate the critical angle for the glass-air boundary. In other words, imagine you've got that This is glass. This is air. You've got a normal line right here. What is the critical angle here? Okay, theta C. What is the critical angle? And when we hit the critical angle, that is going to make the refracted ray go 90 degrees. That angle is going to be 90 degrees. Beyond this angle, of course, if we go just a little bit more, we're going to get total internal reflection. We're going to get that. So we want to know what is the critical angle for the glass-air boundary. Now, I've given you here the index of refraction for glass, the index of refraction for air. So let's see how to solve this problem. So the first thing we do is we write down the equation. N1 sine theta C, the sine of the critical angle, is equal to N2 sine of 90. All right, so it'll be 90 degrees at the critical angle. So write down the equation, and let's see if we can go about solving this. We're going to solve for theta C. All right, so theta C is equal to inverse sine times, and it doesn't matter whether you use a dot or however you like to write this, N2 sine of 90 divided by N1. Okay, so we're going to solve for theta C. We're going to plug in the numbers next. I really like to see this equation here before you start plugging any numbers in, because it shows that you understand what the equation is. All right, so let's start plugging in some numbers. We get inverse sine times N2, which was 1. Remember, it's going from glass into air. All right, so air is the second index of refraction here. This is going to be N2, the second index of refraction. It's going into air from glass. And that's why the glass, there's the 1.0, that's the air. The glass is down below, N1. This is going to be N1, because it's going from glass into air. So N1 into N2 times sine of 90 degrees. Okay, try that on your calculator and see if you get something close to what I get. I'm going to show you what I got. You don't have to look up right now. Just try it on your own. I get approximately 41 degrees. Now remember, the units are right here. Whoops, I missed that a little bit. Okay, the units is right there. All right, this is in degrees. There's no units here. There's no units. There's no units. There's no units there. And don't forget, you're going to have to do the second function and then the sine button, most likely. All right, 41 degrees approximately. That is the critical angle. So if you fire a ray at 41 degrees between this type of glass and this type of air, at 41 degrees, it's going to go 90 degrees. It's going to skim along the surface. If you go 42 degrees as the angle of incidence, you're going to hit and it's going to come back in. All right, so if you were underwater and you were shining a flashlight underwater at 41 degrees, the light ray would skim across the surface. But if you shine the light at 42, 43 degrees, and somebody was outside there, they might never see the ray, okay? Or they would see it maybe hit the surface and not come out to them and bounce right back down. They might be able to see the ray, on an angle because of the particles in the water and stuff, and bouncing off and stuff like that. Okay, so there's your first example problem. All right, let's move on. Example 2, write this down as well. Calculate the critical angle for the diamond air boundary. Now we saw just a moment ago, let me just go back, that if you want to go between glass and air, you got to have a critical angle of 41 degrees. All right, I mean, picture 45 degree angle, right? Half of 90, 41 is pretty close, so it's quite the angle. I should put that straight, and then 41 like that. All right, I don't know if that's helping in any way. Let's try this one. Calculate the critical angle for the diamond air boundary. Now, I'm giving you the index of refraction here. Whoops, and I jumped ahead to the equation. That's all right. For diamond. I didn't write it again for air because it's 1.00. Okay. It's going from diamond into air. So you got your diamond over here. I'm not really going to be able to draw a diamond, so it doesn't really matter. It's just whatever. Okay, there's your diamond. And the idea is that the ray is going, from the diamond, and then it's going to try to come into air. So we want to know at what point, it would just go like that. Okay. Beyond this angle, we're going to get total internal reflection. Now that's important for the diamond because really we want the light to bounce around in the diamond, and that's what's going to give the sparkle. Because it's got a very high index of refraction, all right, and we surpass this critical angle, the ray doesn't come out readily and it bounces around and it gives that glint or glimmer or sparkle to the diamond. You'll see what I mean as we go on. Okay, in order to calculate the critical angle, we write this sort of modified Snell's law, like n1 sine theta 1, n2 sine theta 2. But we know that theta 1, the angle of incidence, is the critical angle. And we know that theta 2, the angle of refraction, is 90. So we go ahead and we write that in. All right. The real important equation, though, is this one. All right. And if you were to skip this first one altogether, that wouldn't bother me at all, because we are calculating the critical angle. What is the critical angle for the diamond air boundary? Okay. Sine theta 1, inverse of sine, times N2. Now that's the second index of refraction. That's the second substance. That's going to be air in this case. All right. Divided by N1, and that's going to be the diamond. So this is going to end up being 1.00, and this is going to be 2.42. All right, so let's go ahead and plug those numbers in, and then you're going to fire up your calculator. All right, so here we see this is the index of refraction, N2, for air. That's the second substance. This is the index of refraction for the diamond, given to you in the question, times the sine of 90 degrees. Okay, that's the angle of refraction we have to have for this to be a critical angle. Now, try this in your calculator. Get used to the order of buttons that you have to press in order to get the answer I'm about to show you. So go ahead and try that, and then I'm going to show you what I got. .4 degrees. Once again, it's in degrees. Well, we're calculating an angle after all. We've got to have units of degrees. Notice that this is a very small angle compared to the glass and air, or the water and air from before. Now, you just have to have a smallish angle, and that's the critical angle. Above 24.5, all right, depending on how the diamond is cut and the light goes through, above 24.4, 24.5, 24.6, 25 degrees, and you get total internal reflection. And the light ray will bounce and bounce and bounce. Okay, so there you go. That's the critical angle for diamond. We're going to try another example, I believe. Okay, well, actually, now that I've done those problems, I have some problems for you to do, all right? Now, in the past, I've done this as a pop quiz. I'm not going to do it this time. I'm just providing you these questions. And here's what I want you to do for your assignment. You're going to complete these questions, write them out, full solutions. They're not all done the same way, all right? I'll walk you through a little bit of this, all right? And then I'm just going to decide, maybe I'll leave it up to my supply teacher if it's a supply teacher today, or if I'm there and I show this video, or your other teacher is doing this with you, let them decide if you want to just try these, you want to collect them, you want to mark them. For now, I just want you to solve these with full solutions so that I can come into the classroom, you can have these all done, and we can take them up. Okay, so let's talk about these problems, okay? So we're not going to worry about this stuff right here, except for the fact that you need full solutions. You are welcome to use your notes, your text, whatever you need, all right? So look at the first one. The speed of light in arsenic trisulfide glass is 1.47 times 10 to the 8th meters per second, okay? This is a velocity, all right? Now, you are looking for the index of refraction. Think about what letter that is. N. So you are trying to solve for N. You are given a velocity. What equation do you know links these together? All right, that's the equation that links them together. So you write out the question. Your solution begins with writing N equals C over V, which then equals, wait a second, what's C? I didn't tell you what C is, but C is a constant. You need to learn this. 3.00 times 10 to the 8th meters per second, right? You've got that in your notes somewhere. Now, number 2 says calculate the speed of light in heavy flint glass. We give you N, and you want the speed of light in the substance. So you are searching again for V. Or you're searching for V, not again. You didn't do it before, but you're searching for V. C is a constant, as I just told you. So now you're going to solve for V. You're going to rearrange this equation any way you know how and get V equals something. So you start with the equation, write the middle step where you substitute in the numbers, and get the final answer. These last problems are more along the line of what we've been doing. Okay, you're going to calculate the angle of refraction in air. This is not a critical angle question. This is a Snell's law. N1 sine theta 1 equals N2 sine theta 2, or N1 sine theta I equals N2 sine theta R. And you are searching for theta R. And we've done some of these in class. All right, you're going to have to split this up from the sines. You're going to get that inverse sine. I want you to try this. You'll notice answers are not given. It's as if this is a quiz or a test, and it's time for you to know how to use your calculator and to just do it. This final question is a critical angle question. All right, solve it just like you solved the other ones. I give you the index of refraction for vegetable oil, and it's starting in the vegetable oil and it's going to air, always from a more dense or higher index of refraction to a lower. Full equation, full middle step, full answer. Okay, so what you can do is you can pause the video at this point, make sure you write down the questions, solve the problems fully, and we'll go on with that in the future. So, hope that helps. See you soon.